Yeah. So we talked about accuracy and precision, and they're not rocket science, although you better be pretty accurate in rocket science. There's a big failure of a satellite once that they plowed into like Saturn or something because they did math wrong. But anyway, you need those in rocket science, but nothing hard so far. Today won't be too hard either. We will learn most of the matching terms. Oh no, it's 66.6 degrees in here right now. Should we just cancel school? It can't be 666 in the room. we should have a kite flying class. Okay, sorry. I have ADD, in case anyone wondered. So we'll learn most of the matching terms. We'll do a little bit of homework. We'll do a little bit of math, and we'll be good. So if you recall, we had just talked about taking measurements. So let's see here. You take a minute. I'll turn the lights off. You and your lab partner discuss what would be the most correct way to report this measurement that you see on the screen right now. So just take a minute. It has to do with our sig figs. It's everything we know and then one number that's a guess. So tell your partner. And then do me a favor, write that number down somewhere. Write down if you think it's A, B, C, or D. Anywhere you want. It's not in your lab book. Just write your letter anywhere you want. What do you guys think? Yeah, what letter? Okay. Green. That one? Okay, good. What letter? Oh, no, that's not what I thought. Okay. It looks like most people are putting the same answer over here on this side. All right. Otter, can you even see it? I got my splitter and it doesn't work. So much for that idea. Okay. Most people put B, 20.0. Who had B? All right. Who had A? Anybody? And then C or D? Raise your hand. So we all had B or D, and both of those are correct answers. Good job. So you could say it's right on 20, then your guess is 0, or you could say, I think it's a little under 20, so it's 19.0, but we should absolutely have two numbers and then one after the decimal to indicate that I knew it was accurate to the tens. I knew it was 20, and you could put 20.1 and still be fine, but you had to have that number after the decimal. Okay, here we go. What is this measurement? I'll move it up a little higher. Uh-oh, they're not grouped. Hold on. Oh, let's see. Is it that one? Oh, definitely not that button. Okay, never mind. I don't know what I'm doing. I'm going to leave it where it's at because that points right where I want it to be. So write that number on the bottom of page 2 or 3 for me. What you think this measurement is. And I can turn this, you can see right there. That is a very light pencil, Pugsley. It's okay. It matches the color of your hair, just super light. You already studying for a different class? Yeah. What test you got? Well, it's not a test, but it's like gotcha. Sorry. All right. So look at your lab partner, see if you guys match, or at least you're close. All right, so here we go. I looked, everyone had the right answer except for one, and you were close. So it's 110 and 3, so that's 113. And then my decimal, I know it's between 0.4 and 0.5. Then I know it's past the 7th mark. And then I need to throw in an accurate or an estimated guess. I can't talk. So I don't know, 3? Don't. It could be a 2, it could be a 1, it could be a 9. That's just your estimated guess. I don't know. Might be right dead in the middle for all that. What did you put?
Oh, she was getting mad at me. She's like, why would you put a 3?
It probably is closer to 5 than it is a 3. But I don't know. It doesn't matter. That last digit doesn't matter. What does matter is you had 3 numbers after the decimal. Raise your hands if you had 3 numbers after the decimal. Okay, good. Anytime you read one of these scales, just report it to the 100th place. Now, there are a few of these on the test, and you don't have to be perfect, like a 3, a 5, a 9, a 1, a 0. They all would have been fine right there. But you do have to have the right number of significant figures. All right, thumbs up if you're okay with that. All right, that's most people. All right. So let's see. Let me get rid of this page. If you need more help, this is in your lab book. This is, it takes you to a video with some questions. It's an ed puzzle if you've ever used that. Well, hopefully, I mean, you feel all right about it. It's not required. That's just there if you need more help on that. Okay, I think I tried to cram this in right at the end of the lab. Does that sound familiar? Okay, but most likely it was in a hurry and it was Thursday, right? So I'm going to assume I need to completely reteach it. And this is in the notes there on page number 2. I enjoyed your family's dance on whatever. It was pretty impressive. Brent could work on his lip syncing skills, but besides that, I thought it was on point. All right. Experimental error and percentage error. This is a thing that's pretty important in science. The experimental error is calculated by subtracting the accepted value from the observed value. Now, the experimental error is actually not very useful. The percentage error is what's useful. And I probably said this, but once again, I'm just assuming I'm reteaching it all. So if you go home and you tell your mom, hey, I only missed 2 on my exam today, what is most likely her next question? How many was it worth? Because that's the really important part. If it's out of 2, you suck. Out of 10, it's okay. Out of 100, you did great, right? We need a reference because just being 2 off is not really that important. And that's what the observed, or I need to stop talking. That's what the just plain experimental error is. It's how many you got wrong. But what we really care about is when we compare it, and we do that through a percentage. The percentage error is the comparison of the experimental error to the accepted value expressed as a percentage. So most of the time, I don't know, when I was a kid, I'd get my test back and they'd say, okay, he got 43 out of 52. And the first thing I would do is find my percentage, right? Because that's what mattered to me. So the percentage is a way we can sort of compare it over time into my other tests. So to do that, we have this equation. Oh, never mind, it's coming up. The sign of the error may be either positive, that means the result was too high, or negative means the experimental result is too low. So let's say on that test, I don't even remember the numbers, but let's say I was at 85%. We are used to reporting it that way. I got 85% of them correct. In science, we're more negative, and we would say, I got 15% of it wrong. Okay, so it's the exact same thing. We're just reporting how far we were off instead of how much we got in the first place. So if we're high, that's like you got extra credit. All right, if we're low, it means that you missed points. Okay, so here is the equation. You will use it on your exam. It is given to you on the exam, but you must know how to use it. So the experimental error is, or sorry, the percent error is equal to the observed minus the accepted divided by the accepted. All right, so the observed is what you get. The accepted is what you should have gotten, like the book or the literature, the homework uses that word, or the teacher or something like that. And then once again, we divide it by that and multiply it by 100. And that gives us a percentage of how far we were off from what we were looking for. And you've done this your whole life. There's only one tiny difference. When you did it, you just took your observed, what you got on the test, out of what it was times 100, and that gave you the 85. We want how far we were off. So that's why we subtract first, and that gives us our value. Okay, I think, all right. So to practice this, we might as well do homework problems together. So turn to, I think, page number 12. And the top 5, I think, might be the 5 through 10. But I think the top 5 are on percentage error. Yep, they are. So I'll help you with number 1. It says the literature value of something. The literature value, that would be the book, right? So Green, what's that number say in number 1? It says the literature value is what? Probably. I can't hear you. Did you make noise? Yeah. It's what? I'll just read it. The literature value of the atomic mass of an isotope is 57.9. So would that be what I got or the book told me? The book, thank you. 57.9. And then it probably says something about a student or you got or whatever. And what's the other number? 59.6. The accepted goes on the bottom again, 57.9. And will you type that into your calculators? You can use your phone if you would like. Yep, you're good. All right. Sam was the first one I saw that had the answer. He says 2.93, I'm going to round it, %. How many of you agree that that is the correct answer? I hope that you do, because that is the correct answer. All right, now, if you look at this number, it's a positive value. The positive value is because you got a number that was higher than what you were supposed to be. If this was a negative number, it would mean that you got a number lower than it was supposed to be. Okay, now, there's 2, 3, 4, and 5. Will you just take a minute or two and work through some of those? Make sure to include the sign. If you get a negative number in your calculator, make sure and put the negative sign. So try 2 through 5. This water bottle, like, bottom was in my room the other, like, Thursday. Anyone lose theirs? Okay. Oh, I know I didn't. Whew. I thought I was all recorded. Okay, moving on. Okay, I'm going to go quick through here. Most of the matching terms on the test are on this page. So here we go. Units. Without a unit, a number is useless. The meter is the SI unit of length. There are 100 centimeters in a meter. Centi means 100. So that's like why there's 100 cents in a dollar. That's the prefix for 100. Next, area is a measurement of the number of squares. Length times width, that's two things. So that's your exponent is a 2 or it's a square that fit into a two-dimensional object. Volume is a measurement of the number of cubes that fit into a three-dimensional object. Length times width times height, that's 3 measurement, thus the exponent 3. That means it's a cube. The liter is the SI measurement of volume. There are 1,000 milliliters in a liter. A milliliter is the same as a centimeter cubed. Okay, so now, please just know that I suck at drawing and just work through that. All right, if we had a cube, oh, this one's not too bad. That's not bad at all. If I had a cube that measured 1 centimeter by 1 centimeter by 1 centimeter, okay, a perfect cube, 1 centimeter length, width, and height, and I was to fill it with something, that volume would equal a milliliter. That's literally the definition. Really, it's water. How much water fits into a 1 centimeter cubic square or cube. That's the measurement of 1 milliliter. So on your exam, you don't really handwrite anymore, but you can use 1 milliliter or 1 centimeter cubed because they're the exact same thing. Fair enough. Okay. Matter is anything that occupies space. Mass is the amount of matter present. Am I blocking you guys? I keep forgetting. The SI unit of mass is the kilogram, which is defined as the mass of 1,000 centimeters cubed of water at 4 degrees Celsius. That's kind of tricky. But this 1,000 centimeters cubed is 1,000 milliliters. Is that on here? Whatever. Or really, it's a liter. So a kilogram is the mass of a liter of water. They throw in the temperature because I did, because I have to include the temperature because the density of water is different. Now, on the exam or on the front page, one of your matching terms says the mass of 1 centimeter cubed of water. So if I divide this by 1,000 and I divide kilo by 1,000, that is gram. So turn to the front cover for a second, and you'll see letter number 6. A blank is the something, I can't read very well because it's dark, is defined as the mass of 1 milliliter of water at 4 degrees Celsius. So 6, you can fill that in. That's a gram. That's the technical definition of what a gram is. The amount of mass in 1 milliliter of water at 4 degrees Celsius. All right. Next, there are 1,000 grams in 1 kilogram. Kilo is the prefix for, that means 1,000. All right, here we we go. Density measures the amount of matter in a given unit of volume. Let me see here. The units for density are gram per centimeter cubed or gram per milliliter. Density is defined as mass divided by volume. So that yellow on the last page looked good. Density equals mass over volume. All right. My AP kids did a little homework and they had to do some density, and they already proved to me that they are the same as every teenager I've ever taught. Pretend that line goes straight. That's pretty ugly. They had to solve for volume, and they did it incorrectly. Not all of them, but some of them did. So I would like to teach you what I call the Tom circle, because it says T-O-M. Just go with me here. This will save your life, especially if you ever take physics. What this circle is it's a way to not screw up algebra. So you take a 3-variable equation and you put it in these places. The thing on top of the fraction is the thing that goes on top. Then the other 2 parts go in the rest. So this is density and this is volume. You're right that I shorthanded that? Okay, now the value of this, and it really is valuable, I promise, please learn how to use it, is whenever you're asked to solve for one of them, you just cover up what you're solving for and it tells you the expression. So we know density is mass divided by volume. We can also then know that volume is mass divided by density, and mass is equal to density times volume. Now you may think, I'm an 11th grader, I know how to solve for volume, but you do it wrong all the time, even the smartest kids. So I say this a lot. Why think when you don't have to? Okay? Because I know you take volume over and D under, but so many people take volume over and then they multiply by D instead. That's just wrong algebra. But you did it in your head and it made sense. So learn the circle. Whatever it asks for, you cover it up, and then the rest of the math is there for you. If it's next to each other, you multiply. If it's over, one over the other, you divide. Fair enough? Okay, so that is how you can do density math problems. So just like percent error, let's go back to page 12 and let's do some homework in class so that it's classwork and not homework. So problem 6 through 10 probably is on density. So 6A something gram has a volume, whatever, that's just density. Let's do 7 together. Thank you. What volume will a 6.38 gram? Okay, so here we go. I'm solving for volume, which means that I am left with mass divided by density. What does it say the mass is? 6.38, is that what it said? Yes?
Yes.
Okay. What did it say the density is? 2.65. So 6.38 divided by 2.65. I don't need to do any other math. This is number 7 if anyone's lost. And what do I get, Thompson? 2.40. All right, and that's volume. It's probably in milliliters. I'd have to read the problem, but most likely milliliters. Okay, kind of got it? How to use that circle? Pugs, you good? Okay. All right, why don't you try 6, 8, 9, and 10 real fast. And once again, well, I don't know. I walked away.
About 6.38 right here, the mass and the volume.
That's going to be grams, so that's your mass.
Okay.
Grams per centimeters, that's your density.
Okay.
All right, so try those other 4 if you would for a few minutes. With these super long classes, we have plenty of time to do some homework together. Oh, bummer. All right, if you're watching, I skipped 2 slides. Get that, and we're back. I have 1 student still that can't come to school is all. All right, volume is the liter, and then temperature, I never remember how to spell, but it's Celsius. It's not Fahrenheit. It's on the next slide, is how to spell it, I think. That's probably spelled wrong too. All right, so those are the typical things that we use. Now, we're America, so we think we're better. We don't use a lot of those. We use feet, gram. We do use joules. We use things like gallons and Fahrenheit. But in science, we use those. Okay, then these prefixes, kilo means 1,000. Centi means 100th. You put a TH at the end because it's smaller. Those, I think the TH is already there. 1,000th. And then micro is a millionth. And we use these 3 a lot, but they're not really micro ever. Okay. Will you take a minute now? It'll be kind of a little break. If you need to move around, feel free to do so. But take a minute now and put on the front cover where the matching terms are. Go ahead and fill in, if you haven't already, 1 through 9. And first, try it without looking back at any notes to see like, oh, hey, I know that. And the ones you know, put a check mark by. If there's ones that you don't know, then, you know, circle it or whatever you need to do. And like I said, let's take a couple minutes and do that. If you need to move your bodies around, feel free to do so. So once again, we're filling in the front part right along here. So where it says 1 through 9, you're taking what your best guess of what those answers are, and then you can look through the notes. Yeah, and we've gone over all of them. So the kinetic theory it's like a minor thing to learn in chemistry, but it sort of governs every part of chemistry. So it's actually pretty important. So these are the notes at the bottom, not the top 5. We'll talk through there real quick. So there's the tenets of the theory. First is that all matter is made up of extremely small particles. Okay, we call those particles atoms. All right, and between the particles is empty space. So that's what this picture is trying to illustrate. If we drew another one of these, it would just be like right here. Oh my, I cannot live with that circle. Hold on. Let me look straight at the board and try that again. Okay, a little bit better. All right, so this would be another atom. So we'd have these 2 atoms. Between the 2 atoms, it's mostly empty because it turns out that an atom, most of its mass is in the nucleus, but they have electrons in the outside. And the electrons push each other away. That's why the nuclei don't collide. But between here and there, there's really nothing. So almost everything, like your desk, your chair, your shoes, your clothes, it's 99% nothing, which would also mean that you are 99% nothing. There's your warm fuzzy for today. You are nothing, you've really never been anything, and you won't ever be anything. So just dial me up. I'm a demotivational speaker, whatever you need that. But that's on the microscopic scale, but there are trillions and trillions of these, so that's what gives us mass. All right, but mostly we are empty space. All matter is mostly empty space. All right, now, those are the two parts. Let's do the next two, and then we'll do the demonstrations. Number 3, particles are in constant random motion. Things are constantly moving around, colliding with each other, just bouncing randomly. And the motion suggests energy. And anytime we have energy of motion, that's called kinetic energy. Kinetic it's the term that means movement. All right, so the demonstration notes are open here on this slide. So, or that screen, let me switch my video over to this screen. Now, these, I used to have a cool demonstrator, but it just broke. So I now have these that aren't as cool. Hold on. All right, so here we go. What you need to do at the top on number 1, you just write random kinetic motion. That's what you're going to describe. Oh, thank you. Shaylee Taylor in the corner, right? Pearson Young. Taylor, coming at you. Miko. Pugs. I'll get it right to where you need it. David. Congratulations. I think pretty much the entire school made the honor roll, 3rd try. We'll get more of those, I'm sure. If you don't get one today, it's coming, I promise. Oh, I needed to be back over here. Congratulations. Did you literally see the newspaper when you guys made the honor roll? It was like that much. And my wife said, Derek, if you're never not on the honor roll, you are grounded. Literally everyone was on it. Okay, so here we go. I'm just gonna hit play, and what you're describing, oh, I don't wanna hear my voice twice. That was just uncomfy. Hold on. All right, so here we go. This is just an 18-second long video. These are a bunch of BBs in a little dish that's gonna shake back and forth, and we're just gonna watch. And this is falling down bad. Here we go. You're going to describe the motion of those particles. Like that, I thought chemistry was gonna be cool. All right. Well, this is chemistry, kids. Okay. The circle at the end. The program I was using, I didn't have the mouse highlighting thing off. So it's just me clicking it to stop it, but then it made the circle. Yeah, it made it appear as though it was important, but it was not. Okay, so in 1 or 2 sentences, describe the motion of those particles. This is number 1. And the title can kind of give you a clue on what we're trying to get you to see. This is not a perfect demonstration because the Petri dish is not perfectly flat. That's why things roll out of the center. But it's good enough. How does this work? Let's see. It does not. How's that? Okay. Just real quick, see these like white ones right here? Tell your lab partner exactly where those are going to go in the 18 seconds. Do you know? Let's try and watch at least part of that piece right there. That might even be a hole for all I know. Ready? Oh, it was pieces. Oh, okay. I don't know where it went either. Okay. The whole point of that was that possible? No, because in the kinetic theory, the movement of particles is what keyword was in the title. It's random, okay? it's determined by too many different things than to be able to predict it. All right? It depends on the container it's in, how many other things it hits, how fast it hits them, what angle it hits them at, and it's just too unpredictable. So in the kinetic theory, motion is random. All right, Brownian movement now. So that's the title. I need to make it bigger, probably. Brownian movement. All right. So I'm going to, I don't want it to play yet. Okay, here I have small BBs and large copper BBs. Okay, so Brownian movement, and I'll just hit play. This one's longer. I like that. It's alive. Okay, that's probably good enough. All right, well, it'll loop. Now, will you describe, when you write what you write, talk about the movement of the copper pieces. The best one that illustrates this is the like BB-8 looking one right here. Okay, don't play. There we go. So Brownian movement or motion, they're the same thing. So what it is saying is that large particles can move through a fluid because of their collisions with smaller particles. That's Brownian movement. And let's see. Okay, have any of you ever been so bored in class you watched the dust particles in the projector light? Anyone ever done that? Okay, now I'm sure it wasn't this class because it's super fascinating, but I used to, and I'm old enough that we used chalk, so there was way more this dust in the room, and I'd be staring at the projector, and it was a lot different than this. But anyway, you would watch a piece, and then sometimes it would just completely change direction. Have you ever seen a piece of dust change direction? And it changes your life, right, Micah? You're like, how on earth did that just happen? Everything's going this way, and that piece of dust just did its own thing and went that way. I wish I was that free, right? And then you just get in this deep thought about your own personal commitment to life. And you're like, wow, that dust changed me. Well, why did the dust change direction? Tell your partner. David, any ideas? No? Okay. Rix, any ideas? Because it was hit by something. I'll restate that a little differently. The dust particle can only change direction if it is hit by something else. And it's hit by small particles I can't see. Like we can't see the air particles, but literally oxygen, nitrogen, all those molecules must have hit the piece of dust with enough energy to change its direction. We just couldn't see it. So the dust particle would be like this piece of copper, all right? And the air particles would be like these little BBs, and it works its way through over time through the collisions because the particles are moving. So Brownian movement, the movement of a large particle through a fluid because of collisions with smaller particles. Now, when you think fluid, you're used to it being a liquid, but a gas is also a fluid. So we don't get Brownian movement between two solids. Like I can't just wiggle this desk enough and have the matches move through it, right? It has to be a gas or a liquid for that to work. Okay, so that is Brownian movement. Now, when years ago, like hundreds of years ago, someone decided to look at milk through a microscope. And if you look through milk or through a microscope at milk, it looks as though it has living things in it. And fresh milk from a cow will, but the milk that most of us drink is completely dead. But it looks alive because the fat molecules, which we can see, are colliding with water particles that we can't see, and the fat, it will move a little bit around. It looks really gross. They call it the dance of fat. And I used to make a joke, but then I got in trouble for it. But it had to do with Bear River. Don't worry about it. But so the dance of fat, what? Don't. Nope, I can't. I'll end up on that page. All right. No. Anyway, it made it, the particles would move around so much they thought milk was living. But then they discovered it was just this Brownian motion. Okay, diffusion or diffusion, I'll say it both ways. It doesn't really matter. So notice here I have some of the darker, shinier ones and then the oxidized white ones. I'm going to turn this on. You can predict first, not hard. Let's have you try and interact with your partner again. Once I start vibrating this back and forth, what do you think will happen? Ready, go. All right, they will all go together. They will all mix is what I heard. All right, here we go. So it's not great. It just kind of spins over time at first, but then they start to interact with each other. I don't know how long I left this going because it didn't work as fast as I was hoping. But you can see that they're starting to blend together, right? Oh, the battery probably came off the lead, I remember. So if we were to leave this on for like 2 hours, we would come back for just a nice homogeneous gray, dark environment. Oh, I want it to end here. I'll just leave it right there. So it's not perfectly blended because diffusion takes time. But when we put two things together, once again in a fluid, which means liquids or gases, they will, because of their motion, their kinetic energy, they will blend together. Okay, so when I was a kid, they taught me about this. And I'm not making this up. In second grade, my teacher taught this, and it was probably her favorite day of the year because she sat in the front of the room and she smoked a cigarette and told us to raise our hands when we smelled the cigarette smoke. I was like, oh, I got this. So anyway, I like these matches, and the way that the air currents are today, it won't be perfect, but raise your hands when you can smell the smoke from this. I'll let it burn and I'll put it out. And it's not going to be a very good demo. Wow, that is like the toughest match to put out ever. Okay, so raise your hands if you smell smoke. So I definitely did. And we all have masks on. You're like, I smell cotton and the perfume or whatever I put on there. Okay, so the front row smelling it. Is that it? Oh man, masks are ruining everything. All right. So I got one person that can smell it. All right, pretend, my good friends. There we go. All right. Really, I'm just testing you all for COVID. So 2 people don't have it. All right. So like I can smell it. Lucy. Okay, now you're making it up because you don't want volleyball canceled. All right. Anyway, that will eventually diffuse. The smoke will diffuse to the whole room. And it might not be strong enough for us to smell through the masks, even though like I smell it crystal clear. But overall, there you go. It will diffuse. Okay, here's a cool, nerdy, and interesting fact all at once. if you exhale, it takes 7 years for your breath to diffuse through the atmosphere. Whoa. So if you've been alive for 7 years, you've taken the same breath as every person on the planet that's also 7 years older. That's weird, cool, and gross. Because, yeah, I won't go into details, but there's other gases you've shared with them too. Well, I'm not going into details. I don't know what you're talking about. Okay, states of matter. We get out of here at 6, is that right? Oh, so should we call it? Okay, because this is like a 5-minute long video. All right. You guys are great. Hey, remember, I know it's weird, but you are my last hour on these days. So you put your desks and chairs nice and straight so Johnny won't yell at me, even though he never has.